The James Webb Space Telescope continues to astonish the scientific community with its discoveries, challenging established theories. A study published in February 2023 presented findings that could revolutionize our understanding of how the universe formed. Surprisingly, the telescope detected at least 6 galaxies whose mass is comparable to that of the Milky Way, located in a region of space that is only 500 million years old after the Big Bang. While the diversity of galaxies in the universe might not seem surprising, this particular fact casts doubt on existing cosmological models. Are our theories about galaxy formation flawed, or should we reconsider the Big Bang theory itself? Thanks to James Webb, astronomers have gained the ability to peer into the previously inaccessible early universe, opening new frontiers for research. Previous works had already reported confirming the existence of the most distant and ancient galaxies, but this latest find could be a true sensation. The article, published on February 22 in Nature, describes the discovery of 6 candidate galaxies that existed just 500 to 700 million years after the Big Bang. The first star clusters were expected to begin forming at the end of the so-called Dark Ages, approximately 400 million years after the Big Bang. In a young universe, no older than 700 million years, it would be logical to expect to see infant galaxies, small clusters of young stars that had not yet merged into large structures. The Milky Way underwent a long developmental journey before reaching its current size and mass, thanks to billions of years of star formation and numerous collisions with other galaxies. Therefore, according to current understanding, galaxies in the early universe should have been 100 times less massive than ours. This new research contradicts that prediction. Some of the discovered galaxies have a mass of about 50 billion suns, which is only half the mass of the Milky Way. Researchers estimate that one of them contains about 100 billion stars, comparable to or even exceeding our galaxy. If these data are confirmed, it would mean that astronomers have found galaxies 50 to 100 times more massive than they should have been at that time, which conflicts with current views on the evolution of the universe. How are such discoveries made? How do astronomers determine that they are observing primordial galaxies and not, for example, a bright star relatively close to us? The most accurate method for determining the distance to distant galaxies is by measuring their redshift using spectroscopy. Cosmological redshift is caused by the expansion of the universe. The expansion of space stretches electromagnetic radiation waves, including visible light, increasing their wavelength. If we could see ancient galaxies up close, they would likely appear as bright blue structures emitting in the ultraviolet and visible ranges. However, due to the immense distance, light from these galaxies travels to us for billions of years, and during this time, the universe expands, stretching the light waves. As a result, the light shifts into the red part of the spectrum, making it difficult to detect. The farther an object is, the greater its redshift. By measuring the redshift of a galaxy or quasar, its distance can be determined. The best way to measure redshift is by analyzing the object's light spectrum. By splitting light into its components, as a prism does, information about the galaxy's composition and properties can be obtained. Astronomers look for absorption lines, gaps in the spectrum that occur due to the absorption of light by atoms of various chemical elements. Knowing which absorption lines correspond to specific elements, scientists can determine the composition of distant galaxies and measure the shift of these lines into the red part of the spectrum. Based on this, the precise redshift value and consequently, the distance to the galaxy can be determined. This method is the most accurate for determining vast cosmic distances and helps ascertain whether the detected object is indeed an ancient galaxy. But what happens next? Will these incredible discoveries be confirmed? And how will they impact our understanding of the universe? Unfortunately, even such a valuable method has an Achilles heel: its complexity. Astronomers must dedicate an enormous amount of time and effort to obtain spectra for only a small number of galaxies. Imagine if we had to analyze images obtained, for instance, from the James Webb Telescope, which might capture tens of thousands of galaxies. In such a scenario, this analysis method becomes highly inefficient. Astronomers simply would not have enough time to study every glowing point. Therefore, spectroscopy is typically used to confirm existing redshift estimates that were predetermined using other, simpler techniques. However, there is an ingenious trick for detecting high redshift objects without resorting to spectroscopy. The secret lies in the fact that even the brightest stars do not emit much light beyond a certain boundary in the extreme ultraviolet part of the spectrum. When searching for the most distant and ancient galaxies, it is logical to assume that these galaxies will be highly luminous due to active star formation. Young stars in these galaxies primarily emit high-energy photons, especially in the ultraviolet range. But there's a catch. This high-energy light from young stars cannot reach us unimpeded. It is blocked by neutral hydrogen atoms, both within the galaxy itself and in intergalactic space. Some high-energy photons emitted by a star are powerful enough to knock electrons out of hydrogen, ionizing it. As a result, light at certain wavelengths from such galaxies simply does not reach us, being absorbed along the way by interstellar or intergalactic hydrogen clouds. A sharp drop-off appears in the star's emission spectrum, known as the Lyman break. This break corresponds to light with a wavelength of 91 nanometers, which is in the extreme ultraviolet part of the spectrum. Consequently, ordinary galaxies containing stars, especially young ones, should have a similar break in their spectrum. What does this mean in practice? We cannot see a galaxy at wavelengths in this part of the spectrum, i.e., at shorter wavelengths, but we will see its longer wavelength emission. Due to the expansion of the universe, light from the most distant galaxies shifts into the red part of the spectrum. Thus, the ultraviolet light from young galaxies reaches us as infrared waves. By analyzing the spectra of such galaxies, we will see that the Lyman break has also shifted from the ultraviolet to the infrared range. In the visible spectrum, or even more so at shorter wavelengths, such a galaxy will be invisible. It turns out that simple filters can be made to transmit light only within a narrow range of wavelengths. Such filters are used, for example, in the scientific instruments of the Hubble Space Telescope and, of course, are installed in James Webb's instruments, particularly in the near-infrared camera, NIRCam, which was used to discover the new galaxies. Some galaxies will be visible through certain filters, while others will not. By changing filters, astronomers can estimate the approximate redshift of each galaxy and therefore, how far away it is from us. This allows for a relatively easy survey of even tens of thousands of galaxies within certain redshift values, without encountering the problems associated with spectroscopic measurements. However, this method is not without its drawbacks. It cannot be considered absolutely reliable, as galaxies vary greatly, and not all of them may emit enough ultraviolet light to create a break in their spectrum. Furthermore, an excess of dust in galaxies makes them dimmer, which can lead to inaccuracies in distance determination. The presence of other sources of redshift, such as gravitational redshift, also affects observational results. This is why astronomers first select the most interesting objects, and then verify their chemical composition and distance using more complex but precise spectroscopy. This is precisely what the authors of the study, to which we should return, were doing. Using various sets of filters, researchers observed a total of 42,729 objects in an image obtained as part of the Cosmic Evolution Early Release Science program. Employing the Lyman break technique and a similar technique called the Balmer jump, astronomers discovered 6 candidate galaxies with redshifts ranging from 7.5 to 9, corresponding to a universe age of 500 to 700 million years. These galaxies will remain candidates until the James Webb Telescope points its instruments at them again and uses its spectrograph to examine their spectra. Spectroscopy will provide precise answers to whether these are truly galaxies and how far away they are. Distance estimates will have an accuracy of up to 11%. It is important to understand that these galaxies are not yet confirmed. They are currently only candidates awaiting confirmation of their reality. Beyond distance, spectroscopy will also show astronomers what exactly is producing all this light in the observed objects, stars, or something more exotic. In their published work, the researchers acknowledge that their conclusions about the mass of the discovered objects might be inaccurate. The bright objects they identified are quite likely active galactic nuclei, AGN, specifically powerful quasars. At the heart of these quasars are black holes relentlessly devouring surrounding matter. Gas, heated to extreme temperatures as it spirals around the black hole, emits a colossal amount of energy. The dazzling glow of a quasar can outshine the light from the galaxy itself, making it nearly impossible to accurately determine its size and stellar composition. Iwo Lab, one of the study's authors, reported in his article for The Conversation that about a month ago, the James Webb Telescope was directed at one of the 6 potential candidates. Spectroscopic analysis confirmed that it is indeed a distant quasar. Thus, final conclusions are still premature. According to the researcher, it will take about another year to study the remaining candidates and establish the truth. However, even if at least one of these objects turns out to be a galaxy, it will challenge our current understanding of the universe. Scientists do not have precise information about when the first star clusters, which later became the seeds of galaxies, began to form. However, as noted earlier, this process likely started within the first few 100 million years after the Big Bang. Over the subsequent 1 to 2 billion years, these early proto-galaxies reached adolescence, transforming into dwarf galaxies. These dwarf galaxies then began to interact and merge, eventually reaching sizes comparable to the Milky Way. This is the generally accepted model. However, if the discovered galaxy candidates indeed possess masses comparable to our own mature galaxy, it could indicate a need to revise cosmological models, particularly the Big Bang theory, or to make fundamental changes to galaxy formation models. For now, we can only state that we are dealing with an intriguing discovery, and the confirmation of these data could cause a real sensation in the scientific world. Nevertheless, it is premature to claim that the early data obtained by the James Webb Telescope disprove